beautifully maintained.
Hello? Oh, it's good. It's good. Hello. My title is Analysis of this access pattern, file systems for content addressable storage. This work is done by Ken Kuniyasu and Yoshihiro. So here I present new virtual block device, just content addressable storage. It's a virtual block device with storage deduplication. So it is used for local servers, but the performance is improved and now it is used on cloud computing, especially on IaaS. So on IaaS, there are many virtual disks for virtual machines. The virtual disks are formatted by file system. The data is stored through the file system. But unfortunately, the CAS is a very strange device. So the affinity between file system and CAS is not clear. So today I want to show the evidence of affinity between file system and CAS. It is an exercise in deduplication storage. So from the evidence, I will conclude we should not use DXT3 on deduplication storage, especially on IaaS. So bad file system is very clear, but good file system is not so clear because there are several candidates. So I show the detail later. This is today's content. At first, I introduced CAS, content addressable storage, and I talked mechanism of deduplication. I also taught localization strategy of file systems. After that, I taught preliminary evaluation of affinity between file system and CAS. Here, I present file deduplication test. Using this test, I evaluate 9 file systems. DXT3, DXT4, XFS, JFS, ReiserFS, Linux, varieties, FAT32, and NTFS. So, I also show the real-based evaluation. I use Ubuntu installed on 5 file systems on CAS, and I will conclude. At first, I introduce CAS, content addressable storage. It's a virtual block device with storage deduplication. On the CAS, data is not addressed by its physical location. It's not addressed by physical address. Data is addressed by a unique name derived from the content. Usually, the name is secure hash. In my case, I use shallow hash. So this figure shows the image. So on the varieties, there are same content blocks. So same color means same content. CAS as an indexing table. Indexing table is a translation table from physical address to unique content name. So there is access to varieties. The access is translated to CAS storage using this indexing table. If the access is to same content, in this case, the negative figure shows the same content. On the CAS storage archive, it is shared by indirectly. So this statement is not so brand new. So plan 9 has 20 features proposed 2002 by using fast. And data domain features bought by EMC has proposed new deduplication technique on using fast 2008. LBCAS local content addressable storage was proposed in Linux Symposium 2009 by us. So, on the CAS, content for deduplication is managed by a unit called chunk. So, according to the size of chunk, CAS is divided in two categories: its size and variable length. So, then have advantage and disadvantage. So its size is very efficient, but its size cannot find the content which do not match to the line. On the other hand, variable length can find any length same content, but it is not efficient. On our case, we want to apply on IaaS cloud computing. So efficiency is very important. So in this talk, we assume CAS is a fixed size chunk. So as an open source software, we have several implementations. Our ABCAS and SDFS are user-space deduplication file system, and ReiserFS open source data duplication for us. In this talk, I use ABCAS, but the result presented in this talk will be the same on other CAS system. So, where is used? So, CAS is used on backup server, but so there are many commercial products. Now, CAS is applied on IaaS because IaaS has many virtual machines and gives many virtual disks. So, fortunately, most people use popular operating system and have same contents. So, we can find the same content on these virtual disks. However, it is not so easy because even if same content are same in the virtual disk, the effect of fixed size duplication depends on how to store data. How to store data on a virtual disk via file system. So, the affinity between file system and CAS is very important. On Linux, we have many file systems. So it's very good because we have many choices. Each file system has each allocation strategies. So each file system works as a filter. The filter changes the location of data by its own strategy. And depending on the location, the effect of deduplication changes. So this slide shows the file systems are used in this presentation. So, can you guess? UXT3, UXT4, JFS, XFS, ReiserFS, Nilbus, varieties, FAT33, NDFS. So, asterisk indicate the loadable file system for Ubuntu. So, each file system has each feature, especially this table shows allocation strategies. So, many file systems use extended allocation. And ReiserFS block set allocation, which is called tail packing. And Linux use the standard file system. So I explain the detail. So deduplication gives continuous physical blocks for a file and reduce fragmentation. This will show the image. So sometimes file system allocate the separated blocks for a file. But extent try to give continuous block as possible. Some block allocation allocate last partial blocks less than 4 kilobytes or multiple files in the single block. This linear shows the image. So most file has a partial block less than 4 kilobytes. So this block is merged in a single block. So this technique can reduce the consumption on the storage. Standard file system is allocate data in a succession from top to tail in a disk. So it is developed to increase the I/O performance. So on the other hand, in order to increase duplication, file system should give some features. So matching, continuous allocation of data blocks, and non-contamination chunks. So alignment matching is the file system should allocate each file to fixed alignment of chunk, deduplication chunk. So at that time, it is easy to be duplicated. Continuous allocations, if 4 kilobyte data is not allocated continuously, duplication will be reduced, especially on a large file system. But this problem will be solved by extent allocation. Non-contamination is if a chunk is shared by file, the chunk will not be duplicated because there are other data in the file. And if 4 kilobyte data block is shared by other file system, for example, circle validation, the duplication will be reduced. So in case ReiserFS will be not to fix the duplication. So we want to evaluate the efficiency of duplication, and we propose file duplication test. So please assume there are 1,000 files which has 1 megabyte of same content. The files are stored on a disk through a one file system, so it will use 1,000 megabyte storage. However, if duplication of cast works perfectly, the files are saved in a 1 megabyte storage. So this figure shows the image. So there is this file system. On this file system, using this file system, data is saved. So here is same content files. So file system works as a filter. So data is allocated on disks with allocation strategies. This block data is separated in a semantic size and created to cache system. In this case, it shows very bad case. So there is not so many same content, except the grand region. This region will be zero clear. On the other hand, if we use very good file system, it is also same. This file system allocate with alignment, continuity, and non-contamination. So we allocate this. This data will be integrated, and there are few chunks in the system. So it evaluates the size of systems. So from here, I'll show the experiment using this evaluation method. So we try to send files to be 1 kilobyte on a 4 kilobyte LB cache. Here we evaluate two chunk size, 32 kilobyte chunk and 256 kilobyte chunk, because we want to evaluate the effect of chunk size. And we try to send 100 kilobyte file is saved 10,000 times. The total storage will be 1 kilobyte. And the second case is 1 megabyte file is saved 1,000 times. Third case is 10 megabyte file is saved 100 times. So last two cases, special case, we try to save 250 kilobyte file to change the data is updated on the region of power of 2. If the file system allocate the file in on an alignment of power of 2, this test will show a special feature. This case is 250 kilobyte file. It is used to compare 256 kilobyte file. If only one 4 kilobyte block is used for metadata or something, it will be used to alignment of power 2. So in this case, the standard file system inputs will lead to this case. So I show the result. So upper graph shows the result on 32 kilobyte chunks. Lower figure shows the 256 kilobyte chunks. So 100 kilobyte files to 10 megabyte. So on this graph shows inputs easy. And pink bar indicates inputs shows what result. And also the ext3 shows that. Most file system also shows that result on 1 megabyte larger files. So continuous allocation is not kept on larger files. And 250 kilobyte and 256 kilobyte case shows there's not so special feature compared to other sites. So Influence stackable file system does not show any advantage on these sites. So, this graph shows the mean level. So we eliminate minus and FP3. We also eliminate 256 case and 252 case. So this line indicates ideal duplication. So in this case, 100 megabyte data is almost duplicated to 100 megabyte storage. So the crossover to the line is data. From this result, we could confirm if anything else, the graph, anything else, good result from both the 32 kilobyte chunks and 253 kilobyte chunks. So, if these four and varieties are good on 32 kilobyte chunks, but on 256 kilobyte chunks, they have not so good performance. This graph shows the conversion between 32 kilobyte and 256 kilobyte chunk. So this graph is calculated from first size on 256 kilobyte chunk is divided by first size on 32 kilobyte chunks. So then shows the degree to reversal on larger chunks. In this case, from 32 kilobyte to 256 kilobyte. The worst case would be 8 times larger. So from this result, Part32 shows durability for larger chunks. So almost 4 times on any file size. But original deduplication is not so good on Part32. So from this result, we summarize. EXT3 and inputs are not good for fixed size deduplication. Then this is good on both chunks and any file systems. But it is Windows file system. And for Linux file system, EXT4 and varieties are good on small chunk size. So this result comes from the file duplication test. From after, I show the real case evaluation. We evaluate installing and looking on Ubuntu 11.04 desktop on CAS. Ubuntu is installed on the different file system. So in this case, the contents are same in the CAS. So we evaluate the future allocation strategy of each file system. So the target file system is here: ext3, ext4, xfs, jfs, and ReiserFS. Here we evaluate dynamic behavior at installing and exporting. We also evaluate static just image. Evaluation function is here. So Ubuntu 11.04 is installed on a 4 GB virtual disk with KVM virtual machine. KVM has 768 MB memory and runs on ThinkPad E400. We compare the effect of 32 KB and 256 KB chunk of LVS. So, as a preliminary statistics, I show the file size in Ubuntu. So in Ubuntu, there is 133,000 files. So, but most file is less than 4 kilobytes. So 77.9% is less than 4 kilobyte file. On the other hand, the total figure shows the volume of files in the storage. So 20.1% is used for less than 4 kilobyte files. So duplication have to deal with these small, many small files. This figure shows access trace of each file system. Red plot indicates new request. Green plot indicates write request. So this figure shows installing, and this figure shows the place of booting. So installing is right-centric operation. Booting is left-centric operation. So it is easy to confirm the data is allocated on a different location. So we evaluate the efficiency of deduplication. So this here shows the installing case. So this figure shows amount of read and write request issued from installer and access data chunk. So blue bar indicates read request and red bar indicates write. Excuse me, it's not a read, it's a write request. So on installing there are many write requests. So the amount request was more than 3 gigabytes, but the total content is 2 gigabytes. So it means the installer issued redundant write request, especially XFS more than 4.5 gigabyte write request. This case is JFS, but it is more than 3 gigabyte. So we analyze the detail. So we analyze the overhead for creating file system. So we evaluate MKFS on each file system. So this figure shows the result. From this figure, we could know MKFS has many loss from the view of images, except JFS. JFS is does not issue so many write requests to images. It means creating file system issued redundant write request. However, the loss at installation is more than 10 gigabytes, so it is not compensated by creating file system. So installer itself has some redundancy. So we analyze static disk image. So this here shows the coverage of each coverage of created chunks. This is the size of disk. So half of this disk is occupied by zero clear chunk. But zero clear chunk has only one chunk. And blue bar indicates non-zero chunk coverage. Red is the result of static 3 kilobyte chunk, and right is 256 kilobyte chunk. There is also the difference between the chunk size. The difference is caused on ReiserFS. ReiserFS is 10% is reduced by tail packing. So with this tail packing works to reduce the consumption of storage from the view file system. This figure shows the result of the indication of each single disk image. So left bar indicates the 32 kilobyte case, and the right bar indicates 256 kilobyte case. So smaller chunk is easy to be indicated. So smaller chunk is much than larger chunks. From this result, we confirm DSD3 and DSD4 have many same chunks. They are duplicated. But the effect is not so big. The effect is less than 80 megabyte compared to 2 megabyte disk image. So there is no big impact in a single disk image. So we should evaluate the ratio of same chunks in other just image. This result will be talked later. So this here shows the result at booting. This figure shows the request issued from operating system booting and the chunks of the request. After booting, there's amount of chunk. Read request is issued chunk has redundant data, so more than chunks have to be read from the system. So in order to solve this problem, we have to optimize to pack a chunk, to pack a data in a chunk. We also present this one at the ASCO 2011 workshop. Please look at the result. Okay. So here I show the relation between just images. I compare the ratio of same chunks between different file systems. We also compare the ratio of same chunks between different installations with same file system. This here shows the image. So solid line indicates compare the different file system. Dot orange line indicates comparison between the different installation of this same file system. So higher ratio is desired. This figure shows the result. So upper figure shows the result between different file system. Lower figure shows the result between different installations same file system. So this result is very interesting. because between file systems, there is no sort of relation. So for multiplied case, multiplied chunks, very small chunk, has high similarity. This size is the file system block size. It is too small for normal chunk for the deduplication storage. On the other hand, the graph shows the results. JFS and ReiserFS gives high cell chunks, even if larger chunks. So in this case, more than 50% is same between different installation. So we guess this result comes from the block allocation divisibility. And we guess ReiserFS is not used deduplication because ReiserFS has a tail packing. But from this result, we guess the tail packing has the identical combination of some allocation. So there is a repeatability of tail packing. So as next challenge, we want to analyze block allocation repeatability. So why there is a block allocation repeatability on the JFS and ReiserFS? Why not on x3 and x2 or XFS? So I don't know if this comes from installer or something. So I want to analyze the as a future work because it is very important to discuss deduplication to get high deduplication. Okay, I want to conclude. So I showed the evidence of affinity in file system and class. So the result indicates if this is not so good for deduplication storage, but there are some candidates for the file system. NPMS was good, but it is not used to good Linux. XT4 was stable on deduplication test and real case, but it was not the best on each evaluation. ReiserFS showed a good result on real case, but we still guess the particular will be a weak point. JFS showed high semi-chunk ratio, but as a result was not so good. But I guess will be candidate for good file system, but it was not tested on real case yet because we cannot apply to bootable file system for Ubuntu 11.04. Okay, that's all.
The question is whether the same file can be deduplicated. For example, if you have many chunks in the same file which are identical, then they're going to be deduplicated. This is the first question. Another question is what happens if your file system is highly deduplicated and sometimes the files are started, someone starts to open files and change their contents, then you may not be able to host all the new data on the file system.
You have two questions. The first question is, okay. So, it's a big problem. We cannot make smaller chunk size. Okay. If we can use byte chunk, we can get a high ratio of same chunks. But for performance, we have to increase chunk size. Okay, so say in a larger chunk, we have to find exact same chunk in the disk. First question is about the efficiency.
My second question was what happens if you have a file system that is highly deduplicated, and so it means that you optimize the storage and many chunks are identical, so you think you have a lot of space and you write more and more data to the file system, but sometimes someone opens the file changes its content, so you can not deduplicate it anymore. I mean, at least part of it. So the requirement from the file system starts to grow. You may need more space in the disk, and you may not have it.
We assume the space of storage is not limited on cloud computing, but it is more important to find same chunks in the cloud storage because we want to reduce the resource for each virtual machine. Okay, so on cloud computing, there's much storage, but we have to also accept many virtual machines. So we have to reduce consumption cost for each virtual machine. Okay, this is answer for your question.
Sure.
Is there any other question? Okay. You know, the reads and write, the reads are quite optimized, as I understand, because you may read sometimes the same data that is already in cache, so you may increase performance there. But on the writes, as I understood, you need to compute the SHA1, the hash for that block. So what is the overall performance impact of doing deduplication of the file system?
Your question is overhead?
Is it faster overall or slower?
So it depends on chunk of size. So if we use smaller chunk, the overhead for SHA1 is comparatively big. So we want to use the larger chunk size to make small index table. So what program is forecast is to make a small index table. So if we can use smaller chunk, we can get a high deduplication. But sometimes the index table become very big. So we want to make small. So please assume if we use 4 kilobyte chunk size, SHA1 we use 20 byte. 25 is about 5%. So it is large to it is very big overhead for management of storage.
But is it faster or slower overall to use deduplication?
So, from the view of deduplication, smaller chunk is better. So, to make fast, you have to use the larger chunk. Because
but compared to a normal file system, would deduplication increase or decrease performance?
The performance is decreased because it's it has overhead to make a small scale system.
Do you have an approximation of the overhead on the CPU?
The CPU, I have no idea.
Okay.
But,
you must have done an install of Ubuntu without a deduplicating file system. And time, how long does the install take? And then you do the same install with a deduplicating file system. How long does that take? What's the difference for an install?
Okay, in this case, we use 250 kilobyte deduplication. At that time, this is very small this is 2000 setup for installation. So, and for loading, the end is 120 seconds. So, usually it goes through at 100 seconds. So, it is a little bit slow, but it will not delay. So, compared to normal file system and normal storage, there's not big exchange. Approximately, there's less than 30% or 5% overhead. Questions?
What are the tools you use to generate your performance data?
How to generate?
What are the tools are you using to generate those data?
So in this case, I use LPCast develop. So the LPCast issued all access log. So we analyze the log.
Okay.
Any questions? Okay, Samuel?